Multi-granularity segmentation prior multiview stereo, or MSP-MVS, tackles the challenge of reconstructing large textureless areas in multiview stereo techniques. This novel method integrates multi-granularity depth edges to restrict patch deformation within homogeneous areas, preventing patches from mistakenly skipping depth edges and calculating areas with depth discontinuity, which can cause ambiguity. MSP-MVS introduces anchor equidistribution, ensuring deformed patches have more uniformly distributed anchors to adequately cover their own homogeneous areas. Additionally, it employs iterative local search optimization to represent larger patches with sparse representative candidates, significantly boosting the expressive capacity for each patch. State-of-the-art results on ETH3D and Tanks Temples benchmarks demonstrate the effectiveness and robust generalization ability of MSP-MVS. By leveraging segmentation images to guide anchor selection within homogeneous areas, MSP-MVS improves the accuracy and efficiency of textureless area reconstruction, advancing the progress of MVS. MSP-MVS builds upon previous MVS methods, including patch match and its extensions, such as cascade architecture, confidence estimators, superpixel planarization, and planar priors. However, it offers a more efficient and effective solution, avoiding complex and time-consuming post-processing or excessively smooth surface details. In contrast to learning-based methods that employ deformable convolutions or adopt a coarse-to-fine strategy, MSP-MVS utilizes lightweight GRU and attention-based feature aggregation to compact 3D volume and enhance prediction quality, making it more suitable for practical applications. Overall, MSP-MVS presents a significant advancement in MVS techniques, offering a more efficient and effective solution for reconstructing textureless areas. Its innovative approach integrates multi-granularity segmentation prior, anchor equidistribution, and iterative local search optimization to improve the accuracy and efficiency of MVS. Multiview stereo, MVS, algorithms, particularly those utilizing patch match-based methods, often struggle to generalize in scenes differing from their training datasets. This limitation stems from fixed patches lacking reliable pixel correspondences. APD-MVS addressed this issue by introducing patch deformation, which reconstructs textureless areas by segmenting surrounding areas into multiple sectors, selecting reliable pixels within each sector, and deforming fixed patches into multiple smaller patches centered on different pixels. However, in complicated scenes, shadows and occlusions can cause anchors to cross depth edges and be selected from heterogeneous areas, leading to potential reconstruction failure. To address this limitation, MSP-MVS is proposed, a patch match-based method targeting the reconstruction of textureless areas. It introduces multi-granularity segmentation prior by utilizing semantic SAM segmentation to extract multi-granularity depth edges, integrating these edges as prior to restrict patch deformation within homogeneous areas. An edge correction strategy based on conditional random fields, CRFs, is presented to better align integrated edges with actual depth edges. The anchor equidistribution strategy is introduced to equip patches with more equally distributed anchors, ensuring comprehensive coverage of their own homogeneous areas. However, this increases computational load, and to address this, iterative local search, ILS, optimization is proposed to represent larger patches with sparse representative candidates, enhancing expressive capability. The contributions of this work include extracting multi-granularity depth edges and integrating them as prior to guide patch deformation, introducing anchor equidistribution to ensure thorough coverage of homogeneous areas, and employing ILS optimization to represent larger patches with sparse candidates. This approach builds upon traditional patch match-based methods, such as patch match, PMS, and GIPUMA, and more recent approaches like ACMM, ACMMP, TAPA-MVS, PCF-MVS, TSAR-MVS, and HPM-MVS. The limitations of conventional and deformable patch match methods in multiview stereo, MVS, tasks are discussed, highlighting issues with memory usage and generalization capabilities. A novel approach, MSP-MVS, is proposed to leverage semantic segmentation and multi-granularity depth edges for enhanced patch deformation. The MSP-MVS pipeline is presented in Figure 2, showcasing a pyramid architecture that integrates several components for improved depth estimation. The method begins by employing the semantic SAM to obtain multi-granularity segmentation images from downsampled multi-view images. These images are then merged and corrected using a conditional random field, CRF, for edge refinement. The corrected images guide patch deformation within homogeneous areas, followed by anchor equidistribution and ILS optimization to select sparse representative candidates for patch representation. The preliminary components of the approach, including the conventional patch-match method and its limitations, are detailed. In this context, the concept of homography is introduced as essential for pairwise matching between reference and source images. The matching cost is calculated using weighted covariance, and multi-view aggregated cost is obtained through view weights. Propagation and refinement steps are applied to update the depth with the minimum cost. The deformable patch-match method, as used in APD-MVS, calculates costs by constructing multiple patches centered around different anchors. However, this approach can lead to inaccuracies due to the absence of depth edge constraints. By introducing semantic awareness and granularity richness, MSP-MVS aims to improve upon these limitations by utilizing multi-granularity segmentation edges for patch deformation. The proposed approach uses semantic SAM to conduct panoramic segmentation on input images, generating masks of varying granularities. These masks are then transformed to derive their boundaries, capturing semantic information at different levels such as scene, instance, and feature. The authors introduce a novel multi-granularity segmentation prior, APD-MVS, to mitigate patch deformation in panoramic segmentation. This approach involves dividing the area into sectors, with central unreliable pixels represented by blue points and anchor pixels represented by red points. The authors employ scene level, instance level, and feature level segmentation images as constraints to obtain different subsets of anchor pixels. The anchor selection process is formulated using equation 4, which filters out anchor pixels whose connecting lines with the center pixel intersect with the boundary map. RANSAC planarization is then applied to the anchors in each subset to determine the optimal distribution of anchors, S max, using equation 5. To enhance robustness, the authors merge different mask maps to form an aggregated segmentation image, retaining labels with the highest count of optimal distribution among internal pixels, as defined in equation 6. The aggregated boundary map BM is derived using the tau function in equation 7, which serves as a new constraint to form a new anchor collection. This process enables the authors to obtain the aggregated segmentation map and achieve robust patch deformation. To address edge blurring and overlapping issues, the authors develop an edge correction strategy based on the conditional random field, CRF, algorithm. The CRF comprises unary and pairwise potentials, representing the probability of pixel assignment and joint probability of adjacent pixels, respectively. The authors incorporate geometric and color similarities for edge correction, as defined in equation 8, where the pairwise potential psi p, Li, Lj, is a function of depth and color differences between adjacent pixels. The algorithm iteratively updates the estimated depth maps, gradually increasing their reliability. By leveraging the multi-granularity segmentation prior and edge correction strategy, the authors aim to improve the coherence and clarity of depth edges, providing more accurate and robust panoramic segmentation results. The authors introduce the concept of anchor equidistribution, a method that improves the reliability of anchor selection in patch-based multi-view stereo, MVS, algorithms. This process involves two key components: sector averaging and anchor clustering. In sector averaging, the homogeneous area of a pixel is divided into 8 sectors based on angle, and the number of reliable pixels in each sector is calculated using the L1 distance between boundary pixels. The average number of reliable pixels is then used to proportionally recalculate the angles and reallocate the sectors. This process is iterated to achieve a balanced division of regions without wastage. Anchor clustering is then applied to achieve comprehensive alignment from anchors to sectors. The authors adopt the density-based DBSCAN algorithm to cluster anchors, which can identify clusters of arbitrary shapes and is robust against noise. The clustering process involves selecting 4 anchors in each sector, applying RANSAC to derive the optimal plane, and then filtering out outliers. The resulting anchor clusters are used for patch deformation, with each cluster comprising multiple anchors and their patch sizes set to balance attention. To address potential memory inefficiency due to varying anchor numbers and patch sizes, the authors propose an iterative local search optimization strategy. This involves selecting partial candidates with distinct features and high contributions using the iterative local search algorithm, which can perform local searching and perturbation to explore potential new solutions. The optimization strategy adaptively selects the best candidates for optimization, replacing the fixed candidates used in MSP-MVS. This approach ensures efficient utilization of resources while maintaining the accuracy and reliability of the MVS reconstruction. The authors introduce a novel method for multi-view stereo (MVS) optimization, referred to as MSP-MVS, which utilizes iterative local search (ILS) to identify sparse reliable candidates for each anchor patch. This methodology is depicted in Figure 5, where candidates are categorized into 3 types: P-blue, P-green, and P-orange based on their characteristics. The ILS function is designed to minimize costs and maximize variance of the profile, as defined in Equation 13. To evaluate their method, the authors utilize the ETH3D dataset and report quantitative results in Table 1. These results demonstrate that MSP-MVS achieves the highest F1 score and completeness compared to state-of-the-art methods, including patch-match-net, ITER-MVS-LS, MVS-TER, EPP-MVS-net, EPNet, PCF-MVS, ACMM, and ACMMP. Additionally, the authors assess their method on the Tanks and Temples (TNT) dataset, providing quantitative results in Table 2. Once again, MSP-MVS showcases superior performance. These results indicate that the proposed method can effectively broaden the receptive field of anchor patches by identifying sparse reliable candidates. The implementation details and experimental setup are also provided, including the datasets used, ETH3D and TNT, and the implementation details of the proposed method. The authors compare their work against both learning-based and traditional methods, providing a comprehensive evaluation of their approach. The authors present qualitative results of their proposed method, MSP-MVS, on partial scenes of the ETH3D dataset, showcasing superior performance in large textureless areas. The method's parameters are set as alpha, beta, epsilon, eta, gamma, micro, delta, upsilon, omega, equals 3, 0.2, 5 times 10 minus 3, 1, 8, 5, 2, 0.2, 0.1. Quantitative results on the ETH3D and TNT datasets are presented in Tables 1 and 2, respectively. MSP-MVS achieves the highest F1 score and completeness on the ETH3D dataset and the TNT intermediate dataset, demonstrating state-of-the-art performance and strong generalization capability. Notably, the method achieves the second-best results in the TNT advanced dataset, with a margin of less than 0.3% in F1 score compared to EPNet. An ablation study is conducted to validate the effectiveness of each proposed component. Table 3 presents the results, which show that the multi-granularity segmentation prior, aggregation, and edge correction are crucial components of the method. The removal of each component leads to notable performance degradation. Specifically, the ablation study reveals that the multi-granularity SAM prior and aggregation are equally important, and edge correction is also essential. Furthermore, sector averaging contributes more than anchor clustering in anchor selection, and the cost component plays a more critical role than variance during candidate optimization. The results demonstrate the effectiveness of MSP-MVS and provide insights into the importance of each component. The method's superior performance in large textureless areas and its strong generalization capability make it a valuable contribution to the field. The ablation study provides a detailed understanding of the method's components and their interactions, highlighting the importance of a multifaceted approach to achieving state-of-the-art results. Accurate scene reconstruction relies on effective constraint patch deformation within homogeneous areas. The proposed method leverages semantic SAM to extract multi-granularity depth edges, which are then aggregated and corrected for accurate patch deformation. This approach enables the preservation of subtle details and structures in the reconstructed scene. To further improve patch deformation, anchor equidistribution is introduced to offer more uniformly distributed anchors, reducing the likelihood of patch clustering and improving overall reconstruction quality. Additionally, ILS optimization is presented to represent patches with sparse representative candidates, allowing for efficient and accurate patch deformation. The proposed method has been validated through state-of-the-art results on the ETH3D and Tanks Temples benchmarks, demonstrating its effectiveness in achieving accurate scene reconstruction. The approach builds upon existing methods in multi-view stereo, including patch match and patch match stereo, and highlights the importance of scene interactivity and object-level scene editing. The extraction of various 3D instances from point clouds using semantic SAM has the potential to facilitate object-level scene editing and improve scene interactivity. The proposed method's novel approach to constraint patch deformation, combined with the use of anchor equidistribution and ILS optimization, makes significant contributions to the field. Future work may involve leveraging semantic SAM to extract various 3D instances from point clouds, enabling more advanced scene editing capabilities. This paper provides a comprehensive review of multi-view stereo (MVS) techniques and their applications in computer vision, focusing on recent advancements. It delves into the challenges associated with traditional MVS algorithms, such as handling textureless regions, large baselines, and varying illumination conditions. The authors then discuss the development of neural network-based MVS methods, which have shown promising results in addressing these issues. These techniques leverage deep learning to predict depth maps directly from input images, utilizing convolutional neural networks, CNNs, and recurrent neural networks, RNNs, for feature extraction and cost-volume regularization, respectively. A notable contribution is the introduction of cost-volume-based MVS networks, representing the probability distribution of depth values for each pixel as a 3D cost volume. This representation allows for efficient computation of depth maps and has been widely adopted in state-of-the-art MVS models. The authors also highlight the importance of geometric constraints, such as epipolar geometry and depth consistency, in enhancing the accuracy of MVS predictions. The paper explores the applications of MVS in various fields, including autonomous driving, robotics, and virtual reality. For instance, the use of MVS in autonomous driving enables vehicles to perceive their surroundings more accurately, enhancing safety and navigation capabilities. Similarly, MVS can be applied in robotics to improve object recognition and manipulation tasks. The authors discuss the limitations and future directions of MVS research, emphasizing the need for more robust handling of complex scenes, dynamic environments, and real-time processing. They suggest that incorporating additional sensors, such as LiDAR or IMU, could potentially enhance the performance of MVS systems. Furthermore, the development of more efficient and lightweight MVS models is crucial for practical deployment in various applications. Overall, this paper provides a thorough overview of the evolution of MVS techniques, from traditional methods to modern neural network-based approaches. It highlights the significant advancements made in this field and underscores the potential for further improvements through continued research and development.